All right, welcome. So this is the first video. The software that I use limits me to 30-minute segments, so I'll probably end up doing probably 2 or 3 videos for the amount of material that we have to cover. But we're starting in section 16.9, and that is waves. So a wave, simply put, is a disturbance. So a wave is a disturbance. Didn't really give myself a lot of room here, but a disturbance that propagates or moves from the place that it was created. The simplest waves repeat themselves for several cycles. We can get into very complex waves, but we'll probably not do too much craziness in this course. So we'll talk about a few things about them, though. But starting with, say, the wave has something called a period. So the period of the wave, and that is denoted by t, the variable t, is an amount of time that it takes for one, say, the peak of the wave to move and be replaced by the next peak. So it's the amount of time for one whole wave length, or one whole wave, to pass. Or for one whole cycle, or whatever it is that we're looking at. It's the wave moves is replaced by the next one behind it. And then we also have something called the frequency, and that's given by an f. The frequency of a wave is the same thing as just 1 over t. It's the inverse of the period, but that's the number of cycles that pass by in a given amount of time. So number of cycles per unit time. The wave will also have an attribute that will have some velocity. So we have velocity, and we have a subscript of w for wave, but the wave velocity, or the velocity of the wave, is given by lambda over t. And so it's the all right, my bad. We're not there yet. Boop, boop, boop. Just kidding. Well, the next attribute is the wavelength. The wavelength. So if I have a very simple wave is just this, the distance between one, wow, I'm bad at this, one top and the next one, this is the wavelength. It's just the distance between two equal or equivalent places on the wave. And so it is just the distance between the two subsequent maximums. Or minimums, right? It doesn't have to be maximums. You can say, well, this minimum and the next minimum, we're going to have that same wavelength. Or you can say this little spot right here corresponds to being this spot on the previous wave, but that length is always going to be, on a simple wave, is going to be the same. And that wavelength is given the symbol Greek letter lambda. And now we can talk about the velocity. And so the velocity of a wave is lambda over t. But since 1 over t is frequency, this is the same thing as just simply lambda multiplied by that frequency. So we're asked, calculate the velocity of wave propagation. There's a goal in the ocean. There's a picture here that goes along with it. Snag this puppy and throw it right here. Oh, come on. So calculate the velocity of the ocean wave in figure 16.30, which is right here. The distance between the wave crests is 10 meters, and the time for the seagull to bob up and down is 5 seconds. And so, get my pen here. All right, then we just have to plug this into that wave velocity is equal to lambda over t. And lambda is that distance here. It's the distance between one wave and the next one, which is given to us as 10.0 meters. So it's 10.0 meters for lambda, divided by the amount of time that it takes them to go bob up and down, to go up and then back down. That's one period. And so I just divide that 10 by 5.00 seconds, and I end up with just 2.00 meters per second. If you need to pause this at any time, go ahead and do so. I'm going to sort of try to move without a whole lot of pauses, again, because the software only allows me to record 30 minutes at a time, and I don't want to do 800 videos. And I'm sure you don't want me to either. There's two types of waves. In this top one, this is a transverse wave, where the wave kind of goes side to side or up and down, whatever you want to call it. It doesn't matter, but it's kind of snake-like movement. But then the bottom one is a longitudinal wave. So we have transverse, and then longitudinal waves. So there are two types of waves. You can make either one of them using a slinky, but they do behave a little bit differently. Music, our transverse waves, as the strings of like a violin or a guitar get strummed or drug a rosined up bow across. They wiggle back and forth in a transverse way. These longitudinal waves are things like earthquakes have both, but you'll see these longitudinal waves in earthquakes and things like that, and other things. But anyway, let's move on. The next section is 16.10, and 16.10 is superposition and interference. So when two waves occupy the same space, they start getting a little bit weird. You can see maybe in this picture, if I zoom in, there's kind of a crisscrossing pattern of these waves, where some waves are coming in from like top right to bottom left, and the other ones are going from like the left to the right. You can see there's these patterns in these waves, and these waves, when they're out in the real world, they all interact with each other. They slam into each other. They bump into each other. They go along with each other for some time. But most of these patterns can get messy out there. So when two or more waves are in the same place, they will superimpose on top of each other, which means that they'll add. But that's not always, adding doesn't always mean an increase. So for example, if I have two waves that are in phase with each other, is what we would say, meaning that there's a maximum occurring here and here, then like we'll call this wave 1 and this is wave 2, and this bottom thing would be wave 1 plus wave 2 added together. If they're both at a maximum, they're going to constructively interfere with each other and they're going to be twice as big. But if they're also at minimum at the same place and time, then the sum of the two is going to be twice as big in that negative direction. And so these things are constructively interfering, or we call this constructive interference. But they can also destroy each other. So in this one here, we've got two waves, but one is at a maximum at the same place in time that the other is at a minimum, and so that adds up to be 0. But they're also 0 at the same time, which adds up to be 0. Or one of them's half as high when the other one's half as low in the negative, and they all add up to 0, and so they cancel each other out. And so this is called destructive interference. But it's very much more common to see two waves that aren't exactly the same wave. And when they interfere, whatever is positive on this top wave, right, at maximum here, we see we have this maximum here that added to a little bit here, this maximum added, right? But if you get like this negative, it's going to subtract in this area, so you get kind of a lower value, and you get kind of a a messy looking wave, but it's still a wave. So this is just the superposition of two waves that both exhibit constructive and destructive behavior. Now, if we look at a standing wave, like if you've ever had a jug of milk and clunked it down in the refrigerator, you can oftentimes see these waves that don't appear to be moving at all. That happens in I thought of things and now they're gone. It happens in like fluids, but it'll like contain fluids like the milk jug. It happens in stringed instruments. It happens in wind instruments when we talk about waves in the air. But what's essentially happening when we have these standing waves that just don't move is these wave 1 is going in one direction, say to the left. Wave 2 bounces off the side of the container, moves to the right, or if we're talking about a stringed instrument, it reflects off of the end of the string, which is usually bound to something, and then bounces back through. But if the wave 1 adds up with wave 2, wow, that's terrible. I missed almost all of it. But if they're in phase with each other, the maxes happen at max, the minimums happen at mins, they're going to constructively interfere. But then a moment later, at a quarter of a time period later, this wave will have moved to the right. This wave will have moved, or sorry, the left. The top wave will have moved to the left. the bottom wave will have moved to the right, and now they don't quite match up. A max matches with a min here, a min maxes with, and they actually completely destroy each other. And so we can see as these guys move, the top is moving to the left, wave 2 is moving to the right, they just kind of rock up and down. This bit here rocks and then goes up, and then rocks and goes back down, while these guys always add up to 0. And these ones that don't ever move, these are called nodes. The nodes are the parts that don't ever move. That's these things. And then the ones that do, these bits that go up and down and up and down the most, those are called antinodes. So that, and say that. And that essentially is just some wave that just rocks in place. We can see that happening though with a stringed instrument. It's literally a string that is bound on 2 sides, and you can have actually a half a wavelength bound between the 2 sides of the guitar or whatever. And this very first one that fits in there, in fact, you can only have, like on a stringed instrument, you can only have certain waves go along that string, because if it tried to have, say, like a wavelength that was 3/4 of this length, it wouldn't fit in there, and the end is not going to allow motion or movement, right? This thing right here, this node, is stuck there, and therefore that limits the types of the wavelengths of waves that can be created on this string. And so this very first one, where half a wavelength fits in between the 2 ends, is called the fundamental wavelength. And I've had some music people that people that produce music say, well, this isn't exactly how it's referred to in the music world, and that may be the case. I'm not really sure, but once you get one where you can get the entire wavelength in between the ends here, one whole wavelength fits, this is your first overtone, and then you've got the next one gives you that's a wavelength and a half in between those 2. That is your second overtone, and so on and so on. Excuse me. Now, if I have 2 wavelengths that have slightly different frequencies, right? It's hard to see here because it's fairly, they're fairly close. But I start at a maximum at one point, and after some amount of time, I get to a destructive interference. After another amount of time, I get to another constructive. So here, it's constructive. I get this bigger wave here. It's destructive, so it kind of is a very small wave. It's constructive again, so I get this bigger wave. But you can see that in the overall picture here, there's this big wave, and then small, and then a bigger and a small, and that's a terrible drawing, but hopefully you can see that, where it's big for a while, and then it gets to the small during the destructive phase, and then gets bigger with the constructive phase. And you can actually hear this, and if we were in class, I would do this demonstration, and maybe I'll do it the next Monday we meet. But we can take tuning forks that ring with 1 hertz difference, and then you would have this womp, womp, womp sound that you can hear over the 2 different tuning forks. And this is called beats. And beats is, I'm just going to grab this because it's been a while since I've used this pad, and my handwriting looks terrible in it. So I'm just going to steal this. a particular wave. Oh, that's big. Yoink. All right. So the get out of here. If I have a wave, it looks like this. It'll have some baseline, and then the distance off of this is the amplitude, and that's given by a capital X. And so it's important because sometimes you'll see a lowercase, in fact, there's a lowercase x in this value. X, that lowercase is where this thing is in relation to time. This capital X is the amplitude of the wave itself. And so we can create a wave with this function. Little x is the position, the up and down position with respect to time. Capital X is that set value of whatever the amplitude is. And then it's just cosine of 2 pi t over capital T. And again, the small t is time. Capital T is the actual period of a wave. Or we can write that as x cosine 2 pi ft in terms of frequency instead of period. But if I add, say, these two, that's not helpful, these two waves together, let's call this x1 and x2. If I want to add x1 and x2 together and just call it some other x, this zoom is not helpful. That's not helpful. Right? Then I can, and this is just the two. This zoom is just going to not do anything but be stupid. But it's just these two things put together. Sorry about that. It's shifting all over the place. So with the x, which is the two waves added together, is just capital X. And we're assuming that they have the same amplitude. So it's the amplitude of 1 multiplied by its cosine 2 pi frequency. Its frequency is f1 t, plus the amplitude times cosine 2 pi, and then the second frequency times 2. But there's a trig identity where we can add those together, and we get this, where the resultant now is a product instead of the sum, but I've got 2x for my amplitude, so this new amplitude here of this new wave is double, potentially. But it also has dependence on two different frequencies here. It has the average frequency of the two waves, but it also has this component up here that is dependent on this f sub b, where f sub b is the absolute value of the difference between the two frequencies. Welcome back. But so the difference between the two frequencies is where we start seeing this large constructive and then this destructive and then this large. It describes the frequency with which we see that, and that is the Beats phenomena. All right, let's dive into 1611. See if I can't beat the clock here with 6 minutes to go of recording time. So 1611 is energy in waves. So all waves carry energy, some more so than others. Some are quite destructive. That's not helpful. Knock it off. As we can see, here's a, where was this? Haiti, I think. well, I don't know, it doesn't say, but an earthquake runs through and can completely demolish houses, buildings, things like that. These are waves. But I'm speaking to you. You have your hopefully you have your speakers on while you're watching these videos. You've got waves blasting at you too. They're not destroying your house, so they come in all sorts of varieties of energy. But the work done by a wave, this thing is proportional to the force of the wave and multiplied by the distance that the wave travels over, the force of that wave travels over. But this is equal to k times x squared, where k is just some sort of constant that has to do with the wave itself. Right? But rather than going through that kind of math, we're going to start deciding. We decide to refer to these in terms of intensity instead. And so the intensity of a wave is its power over a unit area. And then this intensity decreases as the wave propagates outward, because if you have some sort of disturbance here and then these waves will go outwards, the clearly perfect circles that I've drawn here will have larger and larger areas in which they would be dispersed throughout. We're talking about a three-dimensional, it would be a sphere, so you have the surface area of the sphere, and the bigger those get, the weaker and weaker, the less and less the intensity of that wave that one might experience. So there's a question here. I think we'll be able to get through it. Yeah, I think so. Let's go. The average intensity of sunlight on Earth's surface is about 700 watts per square meter. A, calculate the amount of energy that falls on a solar collector having an area of that. So I'm going to kind of just, do it rather quickly because I'm up against the clock here. So pressure, first off, is energy over time. Power is energy over time. And so this means that in my equation, I equals power over area. I can rewrite this as energy over time over area, or over area times time. And so I can solve this for energy equals I times A times T. And then I can plug these values in. So the energy is 700 watts per square meter is the intensity. I'm going to multiply that by the area, so that's multiplied by 0.500 meters squared was given to us as our area. I'm going to multiply that by 4 hours, and then multiply that 4 hours by the 3,600 seconds that are in an hour. And this is 5.04 times 10 to the 6th. And I can't see because that's behind my camera, but 5.04 times 10 to the 6th joules. All right, I'm going to stop here. This is the end of essentially chapter 16. So anyway, I will see you in a minute for 17.